So let's talk about what's underneath the hood of a spectroscopic instrument. So we're mostly going to talk in this class about IR and UV vis, and we're going to definitely be focusing on UV vis today, or in this video. We might eventually touch on some X-ray stuff. So let's just go through sort of your first cut single beam UV vis experiment. So basically you have a source, you have a monochromator that selects a single wavelength of light, you have a sample, and you have a detector. So to go into a little bit more detail on a UV vis, you have a source. It could be, it's usually a tungsten deuterium, tungsten lamp and a deuterium arc lamp. So that covers the region from 110 nanometers to 400 nanometers with the deuterium arc, and then 320 to 2500 nanometers using the tungsten lamp. So then for wavelength dispersal, you need a monochromator that's made out of something like a prism, which works on refraction, how light, it separates the light into its wavelength components through refraction, and how the different wavelengths move through how they're refracted at different angles through the glass. And then what's more common is a diffraction grating, where you're using diffraction. And the reason, like, the prism used to be more common because prisms are a lot easier to make. But now that we have really good methods of making diffraction gratings, that's definitely the easier way to go. So then you have your sample, just like always, and then you have your detector. And so if you're using a single wavelength of light interacting with your sample, a single wavelength of light at a time, interacting with your sample, then you only need to detect one wavelength at a time. So you would use something like a photomultiplier tube. So this is basically where you have a photon coming in, interacting with the photosensitive cathode, and the result of that interaction is that you have an electron. And the electron is pulled away from the photosensitive cathode towards a dynode, which is more positive. It has a positive voltage of 90 volts from the photocathode, and so each of these dynodes is at 90 volts greater, more positive voltage than the last. So every time one electron hits a dynode, there's more electrons that are expelled or that are released from that dynode, and then so you have a multiplication effect, and that's so that by the time you get to the anode, you have a ton of electrons, and you can get 10 to the 6th amplification. So amplification by the time you get to an anode, and then you can measure the current of the electrons that are being that are impacting the anode, and that's how you make your measurement. So let's talk in a little bit more detail about a monochromator, and we're just going to talk about a diffraction grating monochromator because that's what's most common. So basically what you have is white light, or many wavelength light, coming in through your entrance slit. Then it reflects off of a concave mirror, and then you end up with collimated light, which means that the light is parallel. The photons are now traveling parallel to one another, as shown here. And so then it hits the diffraction grating. The different energies or wavelengths of light diffract at different angles, and so those go up to another collimated mirror, and that mirror focuses a single or a narrow band of light of almost all the same energy onto the exit slit. And so if you're looking for the red light, you put the diffraction grating at such an angle so that the red light is what's focused onto the exit slit. And so that's how a monochromator works. All right. So if you were using a single beam or like a single beam instrument, like what I showed on the first little whiteboard, you would have to take your reference in. You'd have to put your reference in. So whatever your analyte solution is in a similar cuvette and whatnot, you'd have to put that in as a blank for the instrument, and then you would have to put your sample in and trade that back and forth. So there's actually a little bit trickier way to do this, where you're using a double beam instrument. So here you have the same source and monochromator, But after the monochromator, you have a physical chopper. This is like a little, looks like sort of like a little pinwheel that goes around and around. And it chops so that sometimes the beam goes to the reference, and there's a mirror here and a mirror here to reflect the light into the reference channel. So sometimes the light goes through the sample just like in a single beam experiment, and sometimes it goes through the reference. And then those two beams, regardless of whether it went through the reference or through the sample, you're going to have the light going into the detector. Here's a mirror that can allow light to go straight through, but it'll also reflect it. So that's how a double beam instrument works. All right. So that's sort of a crude. The instruments I've shown you so far are pretty crude, in the sense that you have a monochromatic source and you're detecting just one wavelength at a time. But with the advent of basically really cool electronics, you can use semiconductors, so a PN type material, to have a multi-channel advantage, which is much faster and much better in general than a traditional single or double beam instrument. So here's basically what you have is a source, and so you have a lot of, that can be a multi-wavelength source like the sun or like an incandescent light bulb, interacting with the sample, and then it goes through an entrance slick, gets focused on some mirrors, and then onto a diffraction grating, and then if you have, and then you have something like a photodiode array, which is basically a one-dimensional strip of where there's all these different little pixels that are photosensitive. So on this pixel you're detecting the red, and on this pixel you're detecting the blue light. So you can collect the entire spectrum, or at least a good portion of the spectrum, all at the same time. And then if you wanted to see a sort of a two-dimensional array, you would call that a charge-coupled device, or a CCD. All right. So what happens if you want to not to look at how much of the light is absorbed by the sample or how much is transmitted, but actually if you wanted to look at the fluorescence. And if you want to measure the fluorescence, you can't put your detector over here because you don't want to know what's going through the sample or what's being absorbed by the sample. You want to see what kind of fluorescence you're getting as a result of the light interacting with the sample. And so in this case, you would have a similar source. If you were doing UV-Vis fluorescence, you would have the same tungsten deuterium arc lamp source. But then you have a mono. This is the first mono in the instrument to select a single wavelength. And then you have the interaction with the sample, and then at 90 degrees, because that's the angle at which you're going to have the least scatter, you have your another mono, and then your detector. So this is also, I mean, we're talking about something like a PMT or whatnot. But basically, you can either scan mono 1 and detect at a single wavelength, or you can scan mono 2 and excite at a single wavelength and scan mono 2. So let's look at that in a little bit more detail. So if you want to do an excitation scan, you would scan mono 1 and measure at a fixed wavelength. So that would look something like, if maybe you're scanning an excitation energy, here, the red curve, and you're only measuring emission maybe at the top of this black curve. Whereas if you want to do an emission scan, you want to excite at a fixed wavelength, so say maybe at the top of the red curve, and then scan mono 2 to find out what you have going on. And both of these are really valuable. You want to be thinking about either exciting, you might need to find the maximum excitation energy, in which case you need to do an excitation scan, or maybe you're interested in the emission spectrum. So let's just review about UV-Vis spectroscopy. So if you are looking at a narrow wavelength or a single wavelength, you can use sources like lasers. LEDs give a relatively narrow bandwidth, or maybe a mercury or xenon arc lamp. However, if you want a sort of a broadband, many wavelength response, you would use a combination of a tungsten and deuterium arc lamp. By the same token, if you only want to detect a single wavelength, photomultiplier tube is a fantastic way to do that. That's totally a good way to do that. On the other hand, if you want to take advantage of a multi-channel detection, you would want to use something like a photodiode array or a CCD. And there's a whole variety of instruments that have come onto the market in the last, I don't know, probably 10 years that take advantage of this in very interesting ways. Like you can actually use your iPhone. I think there's an app for that, to use your iPhone as a UV-Vis spectrometer. There's just a lot of different ways to do that. You can use fiber optics as both your source and your detection method. And there's just lots of ways to do that. It's very interesting. Either way, if you need a monochromator, you can use either a prism, which works on refraction, or a diffraction grating, which works on diffraction.